hey everybody, I'm Sid. I'm a second year PhD student here. And I guess I mostly work on building decision procedures in Lean to decide various theories of interest. So yeah, and I've been working a bunch on, or like a bunch of people in our group and more broadly have been working on building sort of decision procedures and the library to reason about bit vectors in Lean. So I'll sort of be speaking about that effort and, like why this is interesting and useful and what we're hoping to achieve sort of in the longer term. Okay, cool. So I want to open by saying that it's like extremely collaborative work, right? And so, yeah, like most of this is sort of happening directly on the Lean repo, but sort of a lot of the work was like initially done by the Lean Focus Research Organization, which is like this nonprofit that like, let's say runs Lean and manages Lean and whatnot. And so, yeah, so Henrik Boving sort of wrote the BV Decide, which is like a fixed width decision procedure for bit vectors. Josh Kloon implemented the LRAT checker, and a bunch of people wrote the Bitvector library, many of whom are in attendance. And yeah, so it's nice because we're just working with a bunch of people to get all of this through, and hopefully we keep doing this. Right. So the first question is, why do we bother with bit vectors in the first place? I realized that I needed to actually motivate this. So roughly speaking, right, it's like if you're trying to do software verification, then this is like the sort of fundamental type, because like within a compiler, you sort of like assume that all of your integers aren't like actual integers, but they're always like bit vectors of a given width. So for example, this is sort of from our semantics of like the LLVM compiler infrastructure, which is something that's used in compilers. And like most of our basic definitions essentially like use bit vectors to define the semantics of an instruction, like bitwise or whatever. Similarly, there's an Amazon project called LNSim, where they sort of formally define the semantics of the ARM instruction set architecture. So ARM defines their semantics in this kind of pseudocode-ish fashion, where once again, all of the primitive types are again just like bits of things. And what the project does is they sort of translate it to Lean. So like all of the sort of ARM semantics have been, shall we say, manually translated to Lean. They're then checked against the ARM semantics by running the Lean code and the ARM assembly code. And then this is used to reason about ARM programs, in particular cryptography programs, to prove their properties, right? Yeah. And finally, there's also a project here at Cambridge called SAIL, which sort of like defines a programming language to reason about instruction set architectures. And so, so again, it's like, so it's sort of like a programming language inside which you can define the semantics of x86 or ARM or whatever. And they've been recently adding support for Lean. So you can take SAIL and compile it down to Lean. And yeah, so like, as you can see, yeah, we've been sending PRs that sort of like adds Lean support for this. And all of this support depends on possessing bit vectors essentially. So that's sort of why we need it. Okay, I'll maybe like show what the definition of a bit vector looks like in Lean in the first place. So a bit vector is defined to have a given width, W, and then it's defined to be like, a number between 0 to 2 to the W minus 1, which is given by the fin thing over there. And so, well, how do we know it's between 0 and 2 to the W minus 1? We just take a proof that it is in fact between 0 and 2 to the W minus 1. Now, one of the things that's interesting about living in Lean is that, yeah, we can define a bit vector this way, but sort of like we get fairly strong performance guarantees by doing this. And that's because like the Lean kernel knows what NAT is. So like NAT isn't like some weird binary encoding or whatever, but like the Lean kernel has special support for NAT, and it sort of uses like a fast implementation of like arbitrary width natural numbers. So this like actually gives us like, shall we say, good performance when we're trying to reduce large terms that involve bit vectors, which is needed if you're trying to do some software verification thing and you're trying to evaluate something in the kernel, right? Like it's pretty important that these things actually reduce and evaluate quickly. So that's sort of like an important thing, because there are alternative representations we could have chosen. We could have chosen to represent a bit vector as a list of booleans, like a list of length n, but this is a poor choice because yeah, it just won't compute correctly and it just won't be fast. Also, by the way, feel invited to interrupt me if you like have a question or something. I'm happy to. Right. Okay. So, first off, okay, so we have, so it's like we have these bit vectors, and now we want to like prove something about them. Right? Like, let's say for all x, we want to show that x minus x equals 0. So sort of like in Lean, the way this just looks is you call this tactic called BV decide, and it just magically like does the thing for you. But then, like how does this tactic work really? So essentially the way it works is it takes the bit vector formula and it then converts it to a SAT problem, which it queries a SAT solver for. The SAT solver then gives a proof that this is unsatisfiable, which is then checked once again by Lean. So that's sort of like the overarching story of how this works. And so, but like what does it mean when we say it's checked by Lean or whatever? So it's like, so the thing that we're actually trying to show is that like for all variable assignments of this expression, when we evaluate it, we get false. But the way it's checked is sort of by running this particular computation where we check that this concrete function called verify BV expr, when we run it, returns true. So I don't know, it's like a proof by reflection or something, right? Where the idea is that where the idea is sort of like this propositional thing that we want to show can be proven by running this program and then like checking that it outputs true. But of course you can ask, okay, what is this mysterious string C? So so the string C is in fact the actual proof certificate, right? Like it's completely bonkers. You just have some random string C, and if it returns true, then like what's going on. Yeah, so maybe just to like give a little bit, yeah, like what sort of an unsat proof looks like. By the way, so the portion of the library that deals with unsat proof certificates is developed by Josh Kloon. Yeah, so the idea is, okay, like we're trying to show some identity like this, right? That like for all x, x minus x is 0 is a tautology. So the way we actually prove it using the SAT solver is we first negate it, and we show that the negation is unsat. And so upon negation, it becomes an existential formula, which we're trying to show using the SAT solver does not have any satisfying assignments. So that's sort of like the strategy. And so, okay, like how do you show that something is unsatisfiable? Well, essentially there exists a proof system called resolution, which is a proof system that has a singular proof rule, where the proof rule says if you have a clause that takes X or A, and you have another clause that takes not that is like not X or B, then you can derive A or B out of it. And like for example, if you have something like X and not X, then you can use resolution to derive false, because X is X or false, not X is not X or false, and you resolve it to get false or false. So the nice thing about this proof system is that it's refutation complete, which is to say if a formula actually is unsat, then a resolution proof exists. So one could imagine that what a SAT solver does is it tries all the cases, and then it produces for you like a resolution proof, which is the string that we saw, which we then check in Lean that this corresponds to the original formula, that it is in fact an unsat proof. But this is not actually what happens. We actually need slightly stronger proof systems. So the idea being, suppose we have this formula and we're trying to consider whether it's unsat or not. Now, one thing that someone could do if you're a SAT solver is to really just substitute X equals true, because this could never harm you, right? Like X only occurs as a positive variable. And so like, because it never occurs negatively, you can just safely assume that it's true. So this is, and there are like lots of tricks like these that SAT solvers actually do. But this is not logically equivalent to the original formula. And so the resolution proof system doesn't actually let you perform things like this, right? But if you're a solver person, you'll say like, like you can't not let me play tricks like this. Like that's how I write a fast solver. So instead, what we choose to do is like, is to sort of like extend the proof system to represent things that are equisatisfiable and not precisely logically equivalent. And so, yeah, so that extension is called RAT. I'm not going to like bother defining it. I mean, I think it's interesting. We can chat about it later if you like. So it's a nice proof system, but like roughly speaking, or no, precisely speaking, the thing that's interesting about this proof system is sort of like all of the tricks that SAT solvers use can be encoded using this proof system, more or less, right? And so therefore the SAT people were happy to adopt it. It's fairly fast to check, which is also nice. Like it's not a proof system that's very expensive to check. Checking time is like polynomial in the length of the proof, I want to say. And moreover, yeah, like anyway, so it's a good proof system, and that's the proof certificate that we actually use from the SAT solver, and that's the one that we check by reflection. Yeah, so that's sort of like how this portion of the thing works, right? However, if you actually write down such a theorem and you ask Lean, hey Lean, what are the axioms this uses? You might see a fairly scary axiom called lean.off reduce bool. So what, so what is this axiom, one might ask? So essentially, like the point is that even that essentially, okay, so the part that checks the proof certificate, even though it's well written lean and whatnot, it would still take too long if it were to be computed in the kernel. So rather, it's really just compiled by the compiler, and we trust the code that the compiler sort of runs, right? So in particular, the function verify bv expert is checked by compiling that and then like running it. So that's sort of the TCB of this whole thing. So you need to also trust the actual compiler. There's an option somewhere that that disables this, but if you do that, some of your proofs may not go through anymore because the kernel dies on trying to check a really large unsatisfiability proof. Okay, yeah. So right, so it's like, so we now trust the actual unsat proof certificate and like what it represents, but there's still a fairly large hole, right? I say that we start from some Bitvector formula and we produce a SAT problem. Like how does this work? What is this? Like how do you do this? So like the idea is that like there's a fairly straightforward encoding where, because a Bitvector is just a finite collection of bits, you can really replace each bit with a Boolean variable, and then that gives you like a SAT encoding fairly immediately, more or less. And so like there are sort of existing solvers. In particular, the one that a lot of BV decides algorithms are modeled on is called Bitwood's law. I'm told this means fiddler of bits or something like this, right? Yeah, and so like they sort of have the state of the art algorithms that we've been adopting into BV decide. So like when we implement it. But okay, so you can ask, well, why should we even bother using BV decide if Bitwood's law already exists and you're just like taking their algorithms and doing a poorer job, right? And roughly speaking, it's because they also have bugs. So this was a recent bug where like there was some bug in the Bitwood's law rewriter that takes the Bitvector formula and produces a SAT problem, right? And so yeah. So that's sort of like why maybe it's a good idea to actually verify all of these translations. But yeah, so whereas for us, like we actually like verify the translation completely, like the full translation is verified, and so that sort of like gives the sort of full trust story, and that's like that's the portion of BV decide that I have mostly written, basically, like the part that performs the translation and the part that sort of pre-processes the formula to make it more amenable to the SAT solver to actually solve. So yeah, like maybe for an example, if you think of multiplication, like multiplication is just like some operation, which is defined in terms of what it does to the Bitvector values as natural numbers. And we then write a recurrence that says how to like expand it out as a circuit. And we then say that, oh, like if you perform the actual multiplication operation and you grab the ith bit, then that result is going to be the same as what you'd get if you were to like build the multiplication circuit and then sort of grab the ith bit from the circuit, right? So that's sort of like how the bit blasting goes, where you take some more complicated operation like multiplication or division, and you reduce it to like simpler operations like addition or shifts, for which you again have bit blasters, right? Like addition is written in terms of an add carry circuit or whatever. So it's like turtles all the way down till you hit some rock bottom thing that just does bit manipulations. Questions? I don't know. Yes.
Why don't you, or like, this was more about the SAT solving in general.
Yeah.
Why is that picked over, for example, like DPLL or something like that? Is that fast?
No. So right. So DPLL is the solver algorithm that solves the thing. But
that's just specific.
Yeah, so the certificate type is independent of the algorithm you use in some sense, right? So DPLL can produce RAT certificates, but sort of the algorithm that the most solvers use right now is CDCL, which can also produce rat certificates. But the thing that sort of gets hard is how do you encode all the crazy tricks that the solver people do inside the rat proof that you produce? Yeah. And that, so like with DPLL, so if you just do DPLL, you can always produce a resolution proof. But if you do something like the pure literal elimination, there's no straightforward encoding of, like, you can't encode that as a resolution proof essentially. Yeah. So the algorithm that you use to solve the formula is different from the unsat certificate, right?
Okay.
Because in some sense, we're not using it as a sat solver, we're using it as an unsat solver.
Yes. Yeah.
Right.
Okay.
So yeah, so the object of interest is the unsat certificate, not the actual model that it finds. Like if it finds a model, then that's actually a counterexample to the theorem we're trying to prove. So yeah, we're actually using unsat solvers. No, that's a good point. Maybe I should. Yeah. Anyway. So right. So bit blasting is a thing where you take this sort of like bit vector based expression and you produce a sat expression that corresponds to it. So the reason it's not direct is because if you think of like a bit vector level expression like multiplication, there are like many circuits that sort of implement that, right, as like a Boolean circuit, and like each of these different circuits may have like different performance impacts on the sat solver itself. And so therefore, so the circuit you choose will like allow the solver to solve the problem faster or slower, more or less. And which circuit you build is sort of like a black art. And when you ask the people who do this for a living, they have intuitions, but they also very often try a bunch of things and they pick which one works best. So that's, yeah. So it's like if you think of addition, you know, like on the bit vector level, it's defined as take the bit vectors, grab their values as, you know, finite numbers, add them up, take modulo 2 to the w, and then convert that back to a bit vector. But you can't actually feed that into a sat solver, right? So you actually build a circuit that computes the ith bit of the output as a sat formulae of the bits of the input essentially, and that's what the bit blaster does. So it shows the correspondence between the arithmetic definitions that we have and the sort of sat formulae that you need to generate, which encodes the same bit vector problem. So that's bit blasting. Yeah. So that's what sort of lets you go from the bit vector theory to the sat theory, to the right. And yeah, you can get like really clever. So like, for example, if you do division, like, you know, like it's something like instead of, when you build the division circuit, instead of like using a, okay, yeah, so like suppose the numbers you're dividing are k bits, then you might imagine that you need k bits of remainder and k bits of like quotient. But instead you can notice that at any stage you only need like L bits of remainder and K bits of quotient, such that K plus L equals W, because it's sort of like, so because it's kind of like as you sort of discover more and more of the quotient, it's like you need less and less of the of the quotient and the dividend, because like every time, like, you know, like you sort of like you peel a bit of the dividend and you put it into the quotient or not, so that way you don't need to like waste extra bits or whatever, right? And so the formula you build that simulates this kind of circuit will be more complicated than if you were to waste extra bits. And so like, and like, you know, in Bitwutzla they just do these things, but for us we need to prove them all correct, right? So it becomes a really entertaining exercise in in sort of like proving these theorems. It's fun, but yeah. Okay. Right. So I'm obligated to show benchmarks, so I will show benchmarks. So yeah, so like one of the things that we're interested in is to sort of like benchmark it on compilers problems. So we have this like fairly large collection of compiler rewrites called instcombine, and there are something like 6,000 odd problems, and basically VVDecide solves like most of the problems from that data set, which is sort of like what we were hoping for, right? Because like we want to use it to like automatically prove compiler rewrites for software verification, and it turns out that like BVDecide is sort of now strong enough to actually do this. We also actually compare against Bitwutzla, and so Yeah, so here it's, I don't know. Yeah, so it's kind of like, like we solve quite a few problems, but we're still not there yet. Like there's still a fairly large gap with Bitwitzla. And most of the gap, as far as I remember, is because like A is that Bitwitzla builds much better circuits than us in certain cases. So that means that like we generate much poorer SAT formulae. And then the other thing is that sometimes the certificates are so large that like on 4,000 of the problems or something, we just time out inside the kernel, because the kernel just like takes a bunch of time checking our unsat proofs and then it gives up. There are also some SMT-lib problems that are so large that that like we spend a lot of time trying to rewrite them. So it's like BV decide comes with a bunch of simplifications to take the original like Bitvector formula and then simplify it. And so on a bunch of problems, we really just wind up like timing out inside the rewriter. And I think right now, like we use simp as the main rewriting engine. So we might eventually have to write some kind of bespoke rewriting engine that's not just reusing simp, but doing something. Yeah. Of course, like this only matters on problems on the scale of SMT lib, right? Where a problem itself could be megabytes large or something. And so, yeah, so like this, yes.
So what rewriting were you in this case?
So like, an example could be if you have multiplication by 0, just make that 0, for example, right? That's a canonicalization that you might do. Yeah, so it's like simplifying and canonicalizing. So yeah.
Is there a like conflict versus multi-factors?
There is a rewrite system that we hope is confluent on Bitvectors. I don't know if it is actually confluent, but yeah. So like we do try to bring it to a normal form, and the BV decide sort of assumes, I think, that stuff lives in this normal form. Yeah. And right, in terms of sort of like lean APIs, we keep track of a table where the columns are sort of various operations that you can do on Bitvectors, and the rows are ways you can like extract out information from Bitvector. So given a Bitvector, you can say, hey, please interpret as a natural number, as an integer, or give me the kth bit or whatever, right? Or give me the most significant bit. And then you have operations like add and sub and neg and abs and whatnot. Yeah. So this is sort of like a table that keeps track of like how many of the interactions we possess, more or less. In some cases, it's hard to like write really sensible theorems. Like, suppose you take a Bitvector and you copy it 3 times and you ask, what does it mean as a natural number? It's fairly hard to say what that means as a natural number or like as an integer. Yeah. So in some cases, we just say, okay, like no theorem is going to be written because there's nothing useful I can say in this case. But in most cases, you can say something sensible, at least in some subset of cases. Yeah. So maybe to give you guys a sense of like, how the API evolves, because like we're still writing the library, right? Like we still have to like catch up to Bitwitzla, but also B, like folks are like using the library, and so we wind up like adding things to the API and whatnot. So I'll give an example. So consider this expression where you have 16 times x bitwise and y, and now like Bitwitzla performs a sequence of rewrites on this before it sort of like builds a SAT formula to help it like reason with this. So it first rewrites it to shift by 4 because that's multiplication by 16. It then rewrites the shift as saying, please grab the like 28 bits and then append it to zeros at the bottom because that's equivalent. So it then pushes the extract inside the bitwise AND. So it says, oh, like extracting out the AND is the same as extracting this and then extracting that. Now, the reason it does this is consider a case where y is some constant, like 1 left shift 31 or something. So now if you grab like the bottom 28 bits, that just becomes 0. And you're then bit masking with 0. So that then becomes 0. So now the whole thing becomes 0, right? So this is like a fairly useful sequence of rewrites to have if you want to like fold, if you sort of like, want to like simplify constants that you have when you're shifting. So, and we had benchmarks that had these kinds of expressions in them. And we saw that disabling the rewrites basically halved the performance of Bitwitzla. So if we have these rewrites, we should theoretically be twice as fast as we are now on these kinds of problems. So Henrik and I said, okay, great, let's implement this. So, okay, we wrote a theorem, one that says, hey, if you multiply by 2 to the power, that's equal to shift left. And then, okay, we have that, but okay. And then we wrote a theorem for the next thing that said, yeah, fine. Like when you shift, it's equal. But now, of course, you start getting random casts because we're now in dependent type land, and Lean doesn't know that W minus N plus N equals W. So first of all, your proofs start getting more complex. And then we write another theorem that says, okay, what, like extraction can be pushed in. Great. So you think we have sufficient amounts of API. And I sent all of these PRs. Then Henrik came back with a complaint. He said, okay, amazing, you have this theorem. Where's its like corresponding symmetric version? So I said, fine, I'll give you the symmetric version. But then we also had another theorem that said that multiplying 2 to the power of I and 2 to the power of j gives us 2 to the power I plus j. And this instantly breaks our notion of a canonical normal form, right? Because you can rewrite the thing into 3 different things. Like depending on how you rewrite it, you can either get 2 to the power I plus j, or you can get 2 to the power I like left shift j, or 2 to the power j left shift I, depending on like, right? So there's, yeah. So which one do you tag as simp? Who knows? So the current decision is, okay, we're going to write a simp proc and we canonicalize it or whatever, right? But again, like it's never easy, because it's like, like you're trying to balance between like writing a fast solver and sort of evolving the API at the same time. And so like, I don't know, it leads to like competing constraints. So this was the final plan we came up with, which was way more than I thought I signed up for it. Something like, yeah, we write lemmas, and then I write some simproc, and then you add more normalizations, and then we extend the API, and then finally, like we get the rewrite or whatever. So this is sort of like generally how it goes. But yeah, so like, I mean, yeah, it's interesting, and it's also fun, but it was, how to say, evolving the API has been much more challenging than I originally thought because of concerns such as this. And I'd like to hear how the MATLAB people decide in these situations, right? Because I feel like MATLAB also has similar issues where different people want different things, but yeah.
I think just Kim figures it out and everyone
Okay, but how does Kim figure it out? That's
Through sweat and tears, I'd say.
What was that?
Through sweat and tears.
Through sweat and tears. Okay, yeah. Interesting, right? Yeah, Kim may be a bit overworked, so we'll see.
Choices in certain structures. Like lists, it picks on operating on indexing on lists, it picks a certain set of VBAC systems, so it gets into the exact non-normal form every time.
Okay.
So it's like no fresh sugar.
Right. I don't know. I think it's important to get it right, but yeah, it's not clear to me what we should do. Proof confluence. Yes. Easier said than done. Yeah. Does MATLAB have a linter or something for confluence?
There exists a linter for confluence, which is not in use because it would flag to me.
Oh my god. Amazing. Can it be restricted to just run on like these collections of lemmas or something? Do you know? Because I would really like to make sure that the Bitvector API is confluent. But yeah, that's true. But, yeah, okay. Yeah, no, it's just.
I think even the confluence checker is just a local confluence checker. So if you have cases in which it doesn't terminate, the checker won't be able to find it. You just say that it's locally confluent.
Right.
Doesn't terminate? Like, yes.
what kind of?
Like in that point, you're just, anyway, you're fucked anyway.
Yeah. But it's more about.
You have more problems. It's not terminating.
Fair enough. Yes. But yeah. So this is a problem that we've been dealing with, and advice would be appreciated, right? Like, yeah, I don't know. Okay. So then there's the decision procedures that I've been writing, which sort of attempt to solve the same problem, but when you quantify over the bit width. So we want to like solve this problem where the theorem is proven in a way that's like actually not for a fixed bit width, but for arbitrary bit width. And so yeah, the TLDR is, yes, we build some kind of finite automata, which is somehow parameterized by a circuit, and we model check it. So I tried finding a good way to explain this, and I did not. So I think you'll have to suffer through my bad way of explaining this. So we'll see how this goes. So yeah, maybe I take a simpler problem wherein we try to show that bitwise AND is idempotent, and I explain like the ideas of the algorithm, and then like you can tell me how I should explain it better next time. So the first idea is, okay, we have this operation called bitwise AND. It takes two inputs and it produces one output. So I can write it as an automata where each of the transitions takes two input and it produces an output. Furthermore, the bitwise AND operation does not have any memory. Like you don't need to remember anything about the previous bits to know how to compute the current bit. So you really just need a single state that's memoryless. But instead of building this automata, what we actually build is we build an automata which is parameterized. So we say that, oh, we have a single transition where given an A and a B, I produce the output A and B, right? So instead of sort of writing like all the combinations, we just keep track of a Boolean circuit that tells us what the output is at this state. So at this state, given these inputs, here's what the output's going to be, and here's where we're going to transition. That's what the automata contains. Okay, so that sort of gives us the meaning of the bitwise AND operation. Now we want to sort of interpret the equality also as an automaton. So the way we do it is we say, okay, suppose you have like 3 equals 7. Now the way I'm going to interpret that as an automaton is I'm going to say, okay, up to the first bit, I know they're equal, so it produces a 1. And then up to the second bit, I know they're equal, so it produces a 1. And then at the third bit, I know they're not equal, so it produces a 0. And then sort of like from the fourth bit onwards, because the numbers up to that are no longer equal, I should just produce an infinite stream of zeros after this, right? So at state I, you tell me if the numbers are equal up, like if I were to truncate up to that location, because where the idea is for any predicate, the automata that denotes that predicate produces an infinite stream, where the value of the stream at any index tells you whether the predicate holds at that index. So here it tells you the predicate holds at index 1. Here it says equality holds at index 2. Here it says no, equality doesn't hold at if I were to truncate here, and it says it doesn't hold if I were to truncate here, right? So the reason we do this, okay, yeah, so that's sort of like how we interpret equality as an automaton. And again, I can write down some automaton, you can stare at it and believe me that this is in fact the right automaton. It's fine. But again, we don't encode the automaton this way. Instead, we encode it as first a projection function that says if you're in this state, what the output should be, and then secondly, how you transition. So we say that if you're in state S and I give you bits X and Y, then if you're in the failure state, continue to stay in the failure state because you already witnessed they're not equal. Otherwise, if you're in the state where they're equal so far, then transition to the state 1, which is the good state if they are equal at this current location, and 0 if they're not. So that sort of, so when you fail, it takes you to the sync state that keeps you here, and otherwise you test at each time you're over here. So that's sort of encoded by these two Boolean circuits, the projection function and the transition relation. So now the thing is, like, essentially to check if this equality holds for all bit widths, all we need to do is to check if the predicate always produces an output of 1, right? Because then that means that when I truncate at any width, the bit vectors are going to be equal, which means that for all widths, the bit vectors are equal. So that's sort of like the proof strategy, where we show that this large automaton that we build, that's comprised by composing the equality automaton with the bitwise AND automaton, always produces output 1s, regardless of what inputs you feed it. So that's sort of like the thing we're trying to verify or decide. And essentially, the idea is to use an algorithm from model checking called k-induction, where first we check that the initial state produces 1 on all inputs. And then we try to prove some kind of inductive invariant that says that on any input, if a state produces 1, then the next state also produces a 1. So this like establishes the thing, right? But then, okay, why is it called k-induction? This just seems to be one induction. So the idea is like slightly more involved. So, okay, so I'm going to call the initial state as naught, which is encoded by a bit vector of length sigma. And then I have the output function, which is a Boolean circuit from a bit vector of length sigma to a Boolean. And then I have a transition function, which given the input and given the current state, gives me the next state. And now I'm trying to say if the machine that's modeled by this always produces ones. So first I check on the base case. So first I just check if on the initial state the circuit gives me the circuit gives me false. That should be false. If it gives me false, then it's a counter example. If it gives me true, then I'm okay. I now proceed to check the inductive hypothesis. So I essentially check whether for all states and inputs, if this is true, then the transition is the projection applied to the transition is true. And so the interesting thing is, because all of these are Boolean circuits, this is in fact a SAT expression. So I actually use Lean's SAT solver to check this expression. So it's like, so the infinite width decision procedure uses the verified finite width decision procedure to produce a proof certificate of the fact that the inductive case holds, which I think is kind of cute, right? Like you can only do this in an environment where you have a verified like finite width decision procedure that you can like repeatedly call. Okay, so now suppose the inductive case says, yeah, sure, it's true, then okay, you're done. But now suppose it says it's false. Okay, what do you do now? Like this doesn't actually tell you that the automaton doesn't produce true. It may not be a property that you can establish by just looking at one step of the transition. So instead, what you now do is you expand your notion of the output at a state. So you say my new notion of output at a state is the sort of output that I used to get at the state, bitwise and with the outputs that I can get from all states that are reachable by taking one step. And so this way, when I sort of recursively apply this procedure, I'll first check it for one state, and in the recursive call, I'll then sort of check it for all states that are reachable in one step from the first state, and so on and so forth. So this kind of like explores one more bit of the input in some sense, right? Yeah. It's proven correct, so you don't need to take my word for it that this is in fact true. I agree that the fact that it works takes a bit of thought, but that's sort of the algorithm, and that's what we do. Yeah, so that's sort of the algorithm that establishes this, and it seems to work well on problems that don't have large constants. But as soon as you get large constants, it winds up building a large state space, and it tends to take a while to actually prove. So to sort of deal with a large constants case, I wound up writing another solver that's based on a different algorithm. So this one solves a fragment of Bitvector theory called mixed Boolean arithmetic, where the idea is you have all of these inner terms, which are sort of purely bitwise, and then you have like linear relationships between them, right? So you have like a linear combination of purely bitwise expressions. For people who want a formal grammar, I give you a formal grammar, but like I think I think the definition is like, yeah, fairly sensible. So this is again one of those cases where we prove something for a smaller bit width, and we then extrapolate to a larger bit width. So first we show that, okay, like for bit width 1, so we first establish the equality for like width 1. Oh, that's an interesting type of, where we interpret the numbers as integers. Okay, so like not as bit vectors. So like this equality should hold when interpreted as ints, or as ints. So then like once it does, it sort of naturally holds for all bit widths. I'll show it by for why it holds for bit width 2. So I write x1 and x0 to be like, x with 2 bits. So essentially we take the original identity, and we then interpret it arithmetically, where x1 x0 is really 2x1 plus x0, right? Like that's what it means if you have 2 bits. And then we get all of the other terms as well. I then grab all the terms that correspond to the 2 times whatever, and I just rearrange the thing. So that gives me 2 times x1 plus y1 minus x1 or y1 minus 2 times x1 and y1, where the minus 2 inside here actually comes from the minus 2 outside here. But I know from here that that's actually equal to 0. And then like the same thing happens on the other terms, right? So that establishes the identity like for everything. And I haven't, or how to say, I just finished proving it, so I haven't like run this particular solver on the compiler's data set. But I kind of suspect that most of the rewrites that we see in a compiler are actually of this fragment, because things like like this rewrite that you see, that it's like, I don't know, it's one that shows up often, that's used to yeah, like somehow rewrite an addition into things or whatever, right? So I'm guessing that this shows up quite often, because the people who write these are people like, the community this comes from is the deobfuscation community. So they like take code that's been obfuscated or compiled already, and they try to like figure out what it means. So they generate these rewrites to like to sort of decompile. But that's really the like, but if you're proving an equality, it doesn't matter which direction you're rewriting in, right? Like, yeah. So I suspect that quite a few of the like rewrites in a compiler will also be captured by this fragment, really. And this is again one of those cute cases where you can use a SAT solver to establish the 1-bit equality. You don't need a SAT solver, like this is not actually expensive, but it's cute that we can do it. And that then sort of like nicely extrapolates to the full thing. Yeah, so this is sort of like the other solver that I just finished verifying. Yeah, so that let's just prove the sort of full thing. There's also like a bunch of work that we've been doing. So for one, Bitvector has like better algorithms to sort of regroup terms that make it easier for the SAT solver. So Alex, who works in our lab, has been implementing that. Louisa, who is in attendance here, has been like implementing a bunch of extensions that build like better circuits to detect overflows. So SMT-lib has a predicate that says, does this addition overflow or not? And that's again useful for doing verification. So yeah, so we've been working on that. Henrik has been going crazy, adding support for every single lean feature that can interact with the Bitvector. So if you now build a structure of Bitvectors, the BV-decide can now reason about this as well, right? So like, which is quite nice. I think he wants to do inductives on simple types next, but we'll see how that goes. Yeah. So yeah. Huh? Like I just mean that with no index or whatever. Yeah. No. Like I want to say like the like if you take a simply typed language and you add like inductives into it, the fragment of inductives that you'd get from that, I think that entire thing, like because you can, yeah. So that's something that he's been discussing. I make no promises on his part. I don't know if he'll do it, but yeah, he's been thinking about it at least. And I think eventually we'd like to get there. Anyway, yeah. So in conclusion, we have BV-decide that decides the fixed bit width segment. We cover sort of all of SMT libs. We're adding coverage for fancier features and like all sorts of crazy rewrites. A bunch of folks here in Cambridge have been thinking about decision procedures for the generic width theory. So if you have thoughts on that, please talk to me, because I'm currently like implementing these actively. There's a bunch of like SMT style algorithms that we can now implement now that we have a SAT solver. And I'm supervising some projects on some of these, and others I plan to do. And if there are SMT like capabilities you want in Lean, please talk to me, because I'd be interested in doing this, and also because I signed up to do a PhD to do this. So yeah, great. Thanks, guys. I think that's it from me. Yeah.
So have you got any questions? Can be like, I was just thinking about
the translation.
Your
automata
linear thing.
Yeah.
It feels like so many different operations can be translated into this. Like you can have shifts and ands, you can put them.
Yeah, exactly. Yes.
So are you trying to make a bunch of rewrites into this as an alternative solving?
Yes. Yeah. So the advantage of this is that like, one of the problems with the model checking algorithm is that like it can build really large SAT formulae that Cadical just times out on, that the SAT solver times out on. The nice thing about this is that like it only needs to establish the fact on like Bitvec1, right? On just like on just the Boolean level. So this is like a much faster solver. So the way I'm thinking about it is anything that can be canonicalized into this will first be tried in with this. And then when we fail, we fall back on the sort of like the slower, more complete algorithm that handles a larger fragment.
What's the complexity of this translation?
Which one?
Like I guess it would just depend.
Yeah. Yes,
Yeah,
we don't know. And once again, on the model checking thing, nobody has any. Okay, if you manage to prove good bounds, please talk to the committee for a Turing award, right? Because like, I don't think anybody really knows, but it seems to work in the real world. So yeah.
I had a question about the k-induction method. Right?
Yeah.
So the way you describe it, it seems like eventually you're kind of hoping you'll find some k that you only need to have a little k step forward.
Yeah.
Do there ever appear examples in practice where you need like a stronger inductive hypothesis, where say to prove something from like W, you need W02 steps back or anything like that, or is that just like not really an issue?
So are you asking to prove W, you need W minus 2 or like? Oh, W divide. Oh, yeah, right. You need only half. So that is a good question. So the thing is like, I don't, how to say, okay, I think here's the best answer I can give at the moment. I don't know. That's an answer I should know. So I will go find the counter example and get back to you because I'm sure one exists. Yeah.
I had when you were benchmarking your solver against Bitvector.
Yeah.
And so you explained some of the difference. So you attribute some of the difference to the kind of circuit that you end up constructing.
Yeah.
And some of the difference to like verifying the certificate you get. Like,
Yeah.
But so basically what portion of failures are from the circuit and like what portion of failures are like verifying the certificate itself?
So something like 7,000 are from rewriting and like 4,000 are from kernel checking.
Okay.
Yeah. So that's sort of, and these numbers evolve daily. Like we benchmark fairly often and we're trying to close the gap basically. Yeah.